Hi, my name is Mela Coffey, and I'm presenting our paper covering dynamic demand with multi-resource heterogeneous teams. Now, before I get into what this title means, I want to start out with an example. So let's say we're in a post-disaster scenario where it can be dangerous for human first responders to traverse the land, but we do need to deliver supplies to people in need. So we envision a multi-robot team equipped with various resources and tasked with delivering these resources to demand. So the team is heterogeneous in that they carry multiple types of resources like bandages and medicine and different quantities of those resources. In our previous work we presented at ICRA 2023, we developed a control policy for this multi-resource deployment using Voronoi-based coverage control approach. In this work, however, we also consider that demand can evolve over time and that demand can move, demand can be injected into the system, and demand can deplete as we serve the resources. So there has been a lot of work related to resource allocation with multi-robot systems. Some related work uses dynamic task allocation, but these don't consider heterogeneity within the team. And then others include monitoring, exploration, routing, and scheduling, but these approaches have to be solved before deployment and can't account for changes in the environment. So the contributions of this paper include adaptive coverage control to account for dynamic demand. We minimize the locational cost, and we show that the demand is input to state stable under our control policy. And then we also provide simulations and hardware in the loop experiments. So I'll walk through a problem setup through an example. So let's say we have 8 robots shown in the bottom left and 3 demand locations denoted by the X's. The X's can be like a group of people needing resources. And next to each robot is the number of resources of type K that robot carries. So for example, this robot here carries 3 bandages and 1 unit of medicine, and this demand location here requires 50 bandages and 8 units of medicine. So recall that our previous work deployed robots to a static demand using a Voronoi-based coverage control approach. Here you see multiple Voronoi partitions on the left, one for each demand location. In that paper, we showed that our control policy allowed the robots to move such that we minimize the individual locational costs. And in this paper, we show that under the same control policy, the robots still minimize the locational cost under a dynamic demand. Now I'll get into how we define the resource dynamics, which is the main contribution of the paper. So first recall that by demand dynamics, we mean that we allow demand to move, we allow demand to be injected into the system, and we allow demand to deplete as the robots supply the resources. So here we define the resource dynamics. We define the demand dynamics as the rate at which demand is injected minus the rate at which robots are supplying resources to the demand. The robot supply dynamics is the rate at which robot I supplies resources of type K. So S.ijk is the rate at which robot I supplies resources of type K to demand J, and it's a function that we can define. And we actually propose a formulation for this S.ijk. So specifically, we propose a formulation that allows resources to deplete based on the relative locations of the robots. So this says that as robots get closer to the demand, they supply resources to that demand faster. And we show that with this formulation, the demand is input to state stable, meaning that as long as the demand injected into the system is bounded, then our robots keep the demand at a steady state. And just a warning, these simulations contain flashing colors. We carried out simulations comparing our approach shown on the left with a simple persistent monitoring lawnmower algorithm shown on the right. And at a certain time, the demand begins to move and demand is injected into the system. And it's a little difficult to see, but we actually keep the demand around 0. And in the lawnmower algorithm, however, demand continues to grow because they can't meet the demand when demand is injected into the system. We also performed a bunch of randomized simulations, both with and without injected demand. And we see that the lawnmower algorithm is indeed able to meet moving demand without injected demand, but it can't meet demand with injected demand, unlike our approach. In our approach, we actually meet demand faster and we keep the demand at a steady state. And finally, we carried out hardware in the loop experiments. Again, at a predefined time, the demand begins to move and demand is injected into the system. Here we let the demand move horizontally from left to right. And again, with both moving and injected demand, we can drive the demand to 0. So thanks so much for your attention and feel free to contact me with any questions.